Hi everybody, this is Tor Storley and I am back with another video. So in this video, part 2 of this series here, or I should say part of this similarity function, distance functions in DuckDB, we're going to now move to the similarity based functions. So as you can see here on my screen, I have, we left off with the Hamming distance, the last video part, the part 1 of this video. Now we're going to be looking at similarity-based functions. So one of these functions is called Jacquard, with Jacquard similarity function. And notice what it does. It measures the overlap between character sets of two strings. So I have some data here below from that table we created, the words table. So here you can see my code. I create a data frame name called Jacquard results. I execute this particular query, get the original, get the typo column, and then use this Jacquard function and pass in the original and the typo, the two words, and then call it Jacquard similarity. And then you can also compute it as a percent here, as you can see. So when you run this and display it, this is what you end up with. You can see here, even though Apple with two P's and Apple with one P, it says 100%, 1.0, if you will. Remember, this calculation takes values between 0 and 1. But if you look at it, it's kind of strange. Why is it 100% matching here? Well, it all depends on how the formula is computed. So if you look here at Microsoft versus Microsoft, that's also 100. Interesting. So let's figure out why that is. Well, I put together a little bit analysis here on the bottom, as you can see here. So the formula says take the intersection of the word and divide it on the union of the word. So if you look at it here, intersection is written like this. And then, in other words, it's the shared characters in both words. And then the union is all the unique characters in both words. So let's look at Apple. Well, Apple and Apple with two P's and Apple with one P, the unique characters is this, right? Because there's two P's that repeats, it's not unique. So what happened is that the unique character in both words is APLE, so that's the intersection. And because there is no other letter here, because this is just a duplicate of this P, that becomes also the union. So therefore you have APLE over APLE, which is 4 over 4, it's 1. So that's 100%. So as you can see here, the missing P doesn't matter because the Jacquard only counts unique characters. So I wrote out this piece here, so you can read up on that, how that happens. So what about Microsoft versus Microsoft? Well, if you look at the letters here, the intersection is MICROSFT, right? So the intersection is this piece, that's 8 characters. And then the union, because the characters in this word and the characters in this word is the same, the only difference is that the C is after the R here, right? And here the C is before the R. But it's still the same characters. So the union therefore becomes the same as the intersection. So it's 8 characters for the intersection, 8 characters for the union. Therefore, the Jacquard calculation becomes 8 over 8 is 1. And of course, you can do the same thing with Amazon here. Let's look at Facebook, why that is a little different. Well, the first word is FACEBOOK, right? And the second one is FAC, no E, BOOK. Now keep in mind, the unique characters is going to be FAC, no E, because that E is not in this word. And then there's going to be B, but there's only one O we need for it to be unique. So we don't need the second O. So you can drop that from both the words here. So therefore, unique characters here becomes FACEBOK, right? And that's 6 characters. So what about the union? Well, The union is not 6 characters because you need to add whatever's missing, and this word has an E in it. This one doesn't. So you have to add the unique characters plus this extra E here. So that becomes 7 characters, as you can see down here. And therefore, the calculation becomes 6 for the intersection over 7 for the union. That's 0.857 or 85.7% for Facebook, 85.7. So that's how you calculate the Jacquard or Jacquard or whatever, however you pronounce it. That's how you calculate that formula. The Jaro and the Jaro-Winkler similarity functions are a little more tricky. They're a little more to it, and it's not so simple. As you can see here from my code, this is the code, and I'll go back and forth on this. But you can see this is the Jaro function, passing the original word and the typo word. And this is the Jaro-Winkler similarity function. So they're all pretty similar in the way you do it. You just supply with the typo word and the original word and call the actual function you want to run. Now we'll get back to why this is 1, 2, 3, 4 here. And the same with this one, which is the prefix bonus. And this is the prefix length. So here is the output. So let's kind of try to build this up a little bit. The Jaro similarity function formula looks like this. It's the Jaro function, and then you add one word and you add the second word. And then you take 1 over 3 times m, which is the number of matching characters, over the length of the strings. So that's the S1 and S2. And then the last portion of this formula here, you see you take the number of matching characters, number of transposition. Remember we talked about transpositions for those distance functions where you switch the letters. How many switches do you have to do in these letters? They will determine the number of transpositions. That's the formula. So as you can see here, the Jaro-Winkler similarity function is an extension of this Jaro similarity function. You first have to compute the Jaro function. You can see it down here, this piece. And then after that, you're going to add this portion of it. So L stands for the length of common prefix up to 4 characters. And that's why I use the substring. So you have like a 1 character, 2 character, 3 character, 4 by doing these substrings based on these words, as you can see. So you're comparing the original word to the substring of the typo word. And then you kind of starting with 1 character, starting with 2 characters, 3 characters, and so on. So you're building up to 4 characters because that's what the formula is specifying here. That would be up to 4 characters, as you can see here. And the prefix scaling factor is typically 0.1. So that's something that is kind of a static number here. And if you look at it up here in my code, you can see I'm using this 0.1 right there. And this one is the Jaro similarity function that I talked about. Now, if you look a little further down here, you can see that you can calculate this prefix bonus by taking the length of the common prefix up to 4 characters times p, which is the prefix scaling factor, which is typically 0.1 times 100. So that gives you this prefix bonus. So that's become part of how good the score will be, this prefix bonus. Here I wrote a little bit out about what it is. So notice the prefix bonus in the Jaro-Winkler algorithm is an additional score boost given to strings that share common characters at the beginning. So the prefixes, in other words. It is based on the observation that people are more likely to type the beginning of words correctly than the end. So you have a tendency to write better character combination in the beginning than the end of the word. So you calculate like this: the length times the prefix scaling factor times 1 minus the Jaro score, which we computed up using this formula up here. So you can see here that this one represents the room for improvement in the Jaro score, which is that 1 minus the Jaro score here. So let's look at a couple of examples here. You can see Netflix, for example, is NetFL, 4 characters, because both write the first 4 correctly, right? 1, 2, 3, 4, like this. So therefore, its a prefix is 4 characters. And if you look up in my calculation table on above here, you can see that this is the prefix length, right? And here's the prefix bonus calculated. So why is this prefix length 2? Well, AP, but then it has an L, and this one does not have an L, it has another P. So the prefix length is 2 here. Spotify, well, S-P-O-T, and then there's an I, but here is S-P-O-T, but then it's followed by an F. So the first 4 is the prefix length, okay? So that will determine how you compute that, as you can see. And then you can stick your values into this formula here. So here you can see the prefix bonus makes this Jaro-Winkler particularly good for autocomplete systems, spell checkers, and data deduplications. So here you can see a calculation. Here's the first string, apple. It's 5 characters. And here's the second string, APLE, 4 characters. So the matching window, you can find that by taking this floor function of the max of the first word or the length of the second word. So the max of that is obviously 5, but because you don't want decimals, you take the floor. So that brings it, when you take 5 divided by 2, that gives you 2.5, right? So you have to drop that half there. So you're getting 2 minus 1 is 1, okay? So that's the matching window, they call it, okay? So for each character in Apple, you can match it with plus minus 1 position in Apple. So in other words, when you compute this, it will count around these letters depending on that score up here. I break it down as A is in position 0, but you can match it between 0 and 1, right? So A, match position 0, so that's fine. What about the P? Well, it can match positions between 1 plus minus 1, so it'd be 0 and 2, right? From 0 to 2. So here you can see it's between just 2 and 4, so it could be 2, 3, and 4 would match if you find any of this, that L in one of those positions in the second word, right? Okay, that's more stuff here you can read up on. So here you can see the Jaro calculation. This is the apple. So these 1/3, apple has 1, 2, 3, 4 matching characters, right? So that's 4. And then you have the length of the strings. And this first apple has 5 characters because it's APPLE. So therefore, that one becomes 5. So it'd be 4/5. The second word has APLE. So that's only 4. So that'd be 4/4. And then the third one, because there's no transpositions here, that 4/5, APLE over APPLE, APLE over APLE, 4/4. And then because there was no transpositions, it's 0. So then it becomes 4 minus 0/4. So that becomes 1/3 times this. 4/4 is 1. 4/4 is 1 times 0.8, 4/5. And that becomes 0.9333, etc. So what are the key observations? There are a couple of them. For example, the Jaro similarity focus on matching characters and their positions with penalties for transpositions. So it's penalized because of if you switch the letters. It provides a foundation score based on character overlap and positional accuracy. And this Jaro-Winkler enhancement, it adds bonus for common prefixes. So you have a tendency to write the beginning of the word correctly. You get a bonus for that. So it's more forgiving, in other words. So the algorithm here then is particularly effective for typos that involves character swaps or missing characters near the end of words, making it well suited for fuzzy string matching in application like spell checking and data deduplication. Okay, very good. So here is some real world examples. This is a fuzzy product search. So as you can see here, I have 2 tables. This one is a phrase, if you will, iPhone Pro Max. And then I have a table that I call products that has these values in it, okay? And then they're going to be compared to this text string right here. And what you do then is you select product name, the query above, which is that phrase, and then you calculate the Levenstein, the Jacquard, and the Jarrow-Winkler similarity functions, as you can see here. Some of these are case sensitive, so you have to use the lower functions to compare them, right? The lower DuckDB function. So finally, you do a final select here, and down here you can see the result output. So when you compared the search term, meaning the iPhone Pro Max, with the values up here, in the table below, you can see how these calculations ended up. So for example, this edit distance here is the length of what you supplied. For example, the iPhone Pro Max has 14 characters. In order for this to turn into this, it's missing characters. Even though you can find the iPhone, but notice it's case sensitive. That's why we use the lower function. So this one is 23 in length, and therefore the missing characters is 9. So the edit distance here for the first one here is 9, and so on. And then, of course, the Jacquard percentage and the Jarrow-Winkler percentages are computed here. And those formulas are a little more extensive to calculate, but we went through it in great detail above. And as you can see, this first one here is an excellent match, as you can see. When you're using the Jarrow-Winkler, it was an excellent match. Okay, so that's one way you can use these functions to, there's a fuzzy product search application here. You can look at the customer data deduplication. And there's also an advanced spell checker, so you can read into this code. There's quite a bit of it here, but I'm not going to spend all the time on this. So that's something you can look at yourself if you're interested. To wrap this up then, you want to make sure you choose the right functions. You want to maybe combine several functions and make sure performance is important, depending how much data you're going to be scanning or trying to run this over. So it's the DuckDB therefore has an offering of these functions that helps you in doing this type of analysis. So make sure you check that out. And finally, what I'm doing in my code here, I simply just clean up and close my connection to that memory database. Okay, I hope you liked this video. And if you do, give me a like and consider subscribing to my channel. That'd be great. So I wish you a happy evening, a wonderful day, depending where you are in the world. And we'll see you in the next video. Thank you so much.